Here. All right, let's start. First of all, my name is Lee, PhD candidate in finance department. Well, this is a review session for your upcoming lab. One thing I talk to and about series, sequence, and power series. Right? Okay. And you guys are here. Hopefully, there will be some of your classmates join us online. You can see their name here, and they can participate as well, give some comment, or if someone joins us. But last time someone did. So I just don't think there's a question you ask there. It's then to them as well. Okay. So here's how I plan. I talked to the professor. Okay. So he told me that the exam is about this chapter and no more. So, and the majority of the problem is going to be about trying to prove the convergence of series. Right? It's not a majority. Like majority of them doesn't really mean like all of them, but there will be a lot of problems about people. Also, don't forget there are also some about power. Right? So Taylor series, uh, uh, Lawrence, right? Yeah. Maybe I remember he told me something like you don't have to remember the Lawrence series where you EQS or sign or something like that. But maybe there's some problem like maybe you ask you why the methodology is not for sign. You gotta know how to do that. Right? So it's basically a Taylor series. So and there's no need to worry about it, but you got to know. Okay. So here's about what I'm going to do. I personally write something. I may be important. I go through the whole chapter and give you some practice problems to then solve it together. Okay? So let us start it from the beginning. So without any knowledge about sequence, we can't talk anything about sequence. Right? So we start with sequence. Actually, we can write it here. And then see. Right. So for a sequence, I don't know how this course is plot, but when I learned calculus, the first thing I learned in part one is to prove the limit of a sequence and then the limit of function. But I don't know why they introduced the limit of the sequence here. Is that important for this?
I think you can determine the convergence of the sequence using the limit, and you do the limit test to find
So
the
do you
convergence
actually
or
have
divergence.
do you actually have to prove like the sequence, the limit of a sequence is something, and you use the very definition?
Oh.
Well, there's no harm for you to know about it, right?
Yeah.
So let's just say for a sequence, right? Just use A of n. I think that's the most common way to express a sequence, right? So A of n, the nth term equal to something, something, something. And we try to figure out if the sequence is convergent or not, right? So if a limit of a sequence really exists, I just say is capital L, then is we call the sequence convergent. Otherwise not. Right? So there's I think the difference between calculus and whatever we learned in math before is really the rigorous definition of a lot of things. As in this case, the limit of the sequence, right? So what does expression really means? Like what do you call it? The limit of a sequence, whether you can verify it or you can prove it's really not, right? So the definition should be like this: for every use this set aside, right? For all the integral greater than 0, there exists an integer n such that for all small n greater than big N, that A of n minus L is smaller than epsilon. Right? So this is the formal definition for a limit of a sequence. Right? So I think you guys know the limit of a function before, right? It's something like this, but a little bit different. But somehow it's very similar because I recall the definition should be like, for the limit of a function approach A, f of x is something L. The definition is for all the epsilon given greater than 0, there exists another called the delta, such that for all the number x minus L smaller than epsilon. Right? Well, the reason I point this out is that there is another series, theorem. There's another theorem relate the function, continuous function with sequence, right? So the theorem, if you can, can have the book, is that if there's a sequence has the limit of an is L, and we know that there's a continuous function that is really continuous at L. It will be yeah, yes. Well, if x if if x is continuous at L, then we have the limit of f a n is actually f of x. So this is the theorem you can use. Well, this is the thing we learned from this chapter. This is something we learned previously. We have the definition of a continuous function, and this is the result we get. of I don't think, I'm not sure if there's going to be proof or theorem in the text.
No.
But,
Yeah.
okay.
No,
Well, I'm just thinking maybe it's a good problem for you guys to practice, like it's part of warm up. So, but don't expect that something like this is a test that is not. But I just think, understand the proof of this theorem, really help you guys know. Just give it a try to be fun. How you doing? I guess nobody is joining us online.
sorry, I confess, like, when the first time someone wrote the proof of a limit on the board, I, like, didn't understand what the symbol, like, what all the symbols mean, or stuff, like, I don't know what's going on. But now I actually know what the symbols mean. So, yeah, great.
Yeah. Well, don't forget, this lecture is going to be uploaded on YouTube, so you gotta check it out. But I believe the exam's tomorrow. But that's not going to help this exam. Maybe next exam too. Maybe I can talk to my director that next time we can do it a little earlier. I'm not sure if I can do it. Okay. Okay. Like I said, it's all about actually there are some of these so for the guys, you can join online. You can, chat there. Here, you can ask me questions as well, so I will answer you guys. Alright? Can you guys hear me? Right. Thank you. Thank you. Thank you. So, for here, like I said, the only thing you need is the definition. So, what is the definition for maybe we're trying to prove that there's a limit of f a n equal to f l, right? So, by definition, how can we prove it? Well, there are a little change from definition. The new sequence is like FA1, FA2, FAN. So usually it's like AN, A2, but now it's changed a little bit, right? So how we prove that the sequence actually converges? We use the definition, right? So by definition, we have to show that for all epsilon greater than 0, right? There exists an n such that for all small n greater than big N, we have the absolute value of an minus fl is smaller than epsilon, right? So in order to prove this, we have to actually find a big N, right? We have to prove there actually exists a big N, which is an integer. Right? How can we prove that it exists? Either we can find actually N, but I don't think that's gonna work. So we're gonna use the thing we got. F is actually continuous at L. We're gonna apply another definition. What is really mean? F is continuous at L. It's the limit x approach L fx equal to f of L. This is the definition for fx is continuous at L. Okay? But we can further express this formula using the definition for limit for a function. Okay? So reading is for all epsilon greater than 0, there exists a delta such that for all x minus L smaller than delta, f of x minus f of L is smaller than epsilon. Alright? So here we combine these two definitions together. Alright? Don't forget what we are trying to prove. We're trying to prove they're actually copy that. Oh, there's another thing we forgot, right? We have AN is actually convergent to L. Okay? So we have another definition for limit is for all epsilon. Well, I'm gonna clarify a little bit for this epsilon, but I'm just write out all the definition. Okay? So for all epsilon greater than 0, there exists an N such that AN minus L is smaller than epsilon, right? This is by that limit AN is actually L. Right? These are the things we know. These are the things we're trying to prove. Okay? Right, now we know that for all the epsilon greater than 0, there exists a delta, right? And for all the x minus L smaller than delta, we have this. And how about we change this epsilon for delta greater than 0? We use this delta, all right? Because we know that it exists a delta, we call it delta 1, right? So for this delta, we call it delta 1. And for this delta 1, there exists an N such that A and minus L smaller equal to delta 1. Right? So combine these two definitions, what we have? We have for all the epsilon greater than 0, there exists an integer N such that if you plug in this x by AN, we have f of AN minus f of L smaller than which really prove I see some confusing face. It's just a warm-up version. I don't think we're going to do it on test, but by combining these two limit definitions, we can really know the difference between the limit for a function and the limit and how we do it. So let's just move on. So for sequence, there are some other things, like monotonic. So it's either increasing or decreasing, right? And there's another thing called bounded. It's called bounded. It's either bounded above or bounded below, but we call it bounded only if it's both bounded above and bounded below, right? And for this two, we have something very important. I mean, this is kind of like the foundation of whole wheel analysis. It's called a monotone, and what I learned is called a monotone converge theory, but in a book it's called a monotone sequence theory, which is the complexity, right? So if a sequence is both monotonic and bounded, it is convergent, right? Remember, the theory doesn't really give you guys an actual limit, but tell you that the limit is actually this. So it cannot help you find a limit, but will guarantee that there is a limit. Right? So you're gonna see why I'm saying this. There's an example in the book. I don't know if the professor talked about it in the class, but I'll read you it anyway. So this is the problem. We're trying to prove or verify if this sequence is convergent or not. How can we do it? Okay, so A2, here, A2 equals to 1/2 2 plus 6, right? Sorry. We have A1 plus 6. Okay. Okay. So A2 plus AN equals to half A1 plus A2 AN plus 6N.
On both the subtraction on both sides.
Okay, then what we got?
And we can get S.
No, I'm not asking about it sequence.
Yeah,
I'm just
and
asking about this. Yeah, AN.
Yeah, so S and minus 1
But still, we got half SN. This 1/2 before.
Yeah.
If you sub, okay, okay.
Let's try
How about you?
that.
Don't worry. I mean, we got times.
My handwriting is good. So just subtract the things to the left side, and we get equal to minus 1/2 A1.
Yeah, A1. Okay.
A1 plus 1/2 A2
Okay.
to A right?
Yeah.
And this guy equal to 3n, right?
3n.
Yeah, so actually A1 is equal to 2.
Right.
So we could got
A2 plus A2 plus AN equals to
yeah
6n plus 1.
yeah 6n plus 1, and I'll keep writing. That's equal to 6n.
Okay.
And then
Oh, actually it's
what?
3n.
3. That's 3n. All right, and we add an A1 here, so that's equal to minus A1 plus 1/2 Sn, right?
Okay.
And that's equal to 3n. So and minus A1 equal to minus 2. So we could get
Yeah. Right there. Yeah, with your hand. With your hand.
okay. So and I think what's that? So actually this is minus 2. So I move it to the right side. So I got 1/2 Sn equal to 3n plus 2, right? And times 2 on both sides, so we got that's 6n plus 4, 6n plus 4, right? And so huh? Times 2 on both sides. Right. So Sn Sn minus 1 equal to 6 times n minus 1 plus 4, right? And subtract this 2. So on the left side we got an, and on the right side we got but that's the method.
I'm not sure it might work, but
Could you tell me where I got math?
that's not the way I was thinking. But
But it could work out. 2, 1.
Can you bring it to the ground? Sorry, sorry.
My handwriting was.
Well, I really can't tell where the problem is, but why?
Well, it's because A2 is equal to 1 half A1 plus 6. So you know H2 is equal to 1 half 2 plus 6, H2 is 1 half A, which is 4. So your answer for A2 has to be 4. And the
Oh,
so,
yeah. What the reason why we're doing this way is when you add them up, each side will cancel out. Or with only one term left, and we can do something like that. But I guess you can think about it when you get home. I'm sorry, this is really not the way I was thinking. But anyway, you can check it. You know,
sorry.
and the way I was thinking is using the monotonic sequence to prove. First, prove the limit really exists, and then try to figure out what the limit is. Right? So, first, in order to apply the monotone sequence theory, we have to first say if it is increasing or decreasing. Okay. So I just write some terms out. A1 is 2, A2 is 4, right? So it's kind of like increasing. Or we can write even more terms if we have 5, right? So it's kind of like it's increasing. So let's just assume it's actually increasing. Well, I assume you guys know about it. Okay, so the first thing is A2 is greater than A1. Then we can actually check, right? The second thing is we assume that AK is smaller than AK plus 1. Then we prove that AK plus 1 is smaller than AK plus 2. Okay? So this is what we got, which is this is what we got. Let me just leave it like that. Okay, for AK plus 1 smaller than AK plus 2, we have AK AK plus 2 equal to what? 1 half AK plus 1 plus 6, right? And we have AK plus 1 is actually greater than AK. So it's greater than half AK plus 6, which is AK plus 1. So that's how we prove that AK plus 2 is greater than AK plus 1, right? So we can prove the sequences actually. How about for bounded? For bounded, we gotta know what the bound is. Well, we can assume that the sequence actually have a limit, which we name it L. Okay? So the limit infinity, an plus 1, which is L, right, equals to limit n to infinity half times an plus 6. So L equals to half L plus 6. Alright, so L equals to 6. So if there actually exists a limit, the limit should be 6. So far we don't know if the limit exists. Alright? And we know that the sequence is actually increasing. And the limit is 6. So the sequence is like increasing towards 6, but never go over 6. So we can assume the boundary is 6. Alright? So we can go back. We use for A1 is equal to 2 smaller than 6. We use mathematical example again. Right? A1 is smaller than 6. So we assume AK is smaller than 6. Then AK plus 1 equal to 1 half times AK plus 6. Remember, AK smaller than 6 is the assumption. This is the assumption. And it's smaller than half times 6 plus 6, which is 6. That's how we get AK plus 1 is actually smaller than 6 plus 1.
So that's smaller than 6 versus 3.
Yeah.
Or merge.
You mean... Yes, what I'm trying to prove is the sequence is bounded. Then combined with what we have proved that the sequence is increasing. Then combine those two, we have the sequence is actually bounded. Right? And we already got a limit. So that's how we solve this problem. But I think or figure out what's going on. Okay. So now we settled for the sequence part. Now we can move to the series, which should be the most important thing in this text. The reason why I think I should focus on sequence first, because series is the original sum of sequence. And the important thing is the partial sum, right? Is I from I to to n ai, which is the sum of the first nth term of the sequence. And we know that this partial sum is actually the thing that help us verify if this series convergent or not. And we know that this S of n is actually a sequence. So that's how we can prove. So in other words, we know if we want to know if a series is convergent or not, we have to prove a sequence is convergent. So that's why I spend a lot of time on sequence first. And for a series, the first thing we know is called the geometric theory of series. Okay. So, can we jump a little, further? This thing close to it. It's a power series. I'm asking you if you recognize something, the formula like this. This is the power series of a function, which is
Yeah, he's asking.
I just want to say.
yeah. Sorry, I'm asking. on the geometric series. X to the n?
Wait, no, it's not? Wait, because x to the 0 would be 1. X to the first would be x.
Oh, you mean this?
Yeah. Yeah, sorry.
Some main-
Sorry.
Okay.
I'm sorry.
But my question is actually this equal to what?
Oh.
Wow.
I just a little, the way you learn is 1 over 1 minus x equals to 1 plus x squared.
Oh.
But I'm asking you this side. And you know that this is from geometric series, right? What is the convergent, the radius of convergent equation?
It must be greater than negative 1 and less than 1.
Okay, so absolute value is smaller than 1, right? Yeah. And this is from geometric series.
Wait, is it 8 over 1 minus 1?
Yeah,
Yeah,
that's what he said.
Okay.
I'm just trying to relate it things, from front and backward. So for geometric series, it's like a, which is the first term, times plus ar squared, something, right? So the partial sum equals to a times 1, ar minus 1. Okay, the partial sum is first term times 1 minus r to the n over 1 over r, okay? So in order to make this sequence convergent, we have to make this term goes to 0, which really means r has to be within 1, right? So that's how we get the radius of convergence for that policy. It's from here. Okay. So there comes another question. Not all the series are geometric series. There are a lot of series that don't have the form for geometric series, but you can ask us whether the series is convergent or not. Right? So I believe in the class, the professor tell you a lot of text, a lot of text. Okay, so first one is okay. That would be convergent test. Sometimes for me, when you ask a student, when I learn this stuff, I never, thinking of using this test, but somehow where some problems it might work, and it will actually save a lot of trouble. So you don't have to answer, basically. You're just trying to verify if the last term is 0 or not. Right? If it is 0, it doesn't tell you anything, but if it's not 0, it's never for sure. Okay? And what about others? Yes, integral test. Integral test. What is test is for? So we use really is something like this, right? To see this properly goes convergent or not. But remember, there are some assumptions for the self of x. First, it has to be continuous, and it has to be positive, and finally, decreasing. So don't forget to check if this function is decreasing or not. If you have time, you can actually do a problem to this. But I'll save it for the last. Okay. So Well, in my experience, for a lot of function, sorry, for a lot of series that can be tested using integral test, can also be tested using ratio test. So, I mean, it's ratio test is always easier. So we don't have to use integral test if we don't have other things to do. And integral doesn't always come up as easy. So this is a backup plan, right? Most importantly, I think in the book is asked you to prove that the P theory is convergent, right? Using integral test. So what is the conclusion for P theory?
Wait, P series is
1 over n to the p.
Convergence, and if it's less than 1 second. Or 1. That's fine.
Yeah, well, that's
For p greater than 1, it's called and p smaller or equal to 1. You can verify this using integral test. So now we move on to something else. It's called comparison test. Right? Comparison test. And I believe there's another comparison test called limit comparison test. Well, I'm not sure what kind of problems in the past, but will the professor give you a hint like use what kind of test for this problem?
He doesn't tell us anything.
no.
Well,
There's just numbers on the page and then go at it.
Yeah, he's so small.
Yeah, pretty much.
well, I guess you guys have to find out. It's the best way to do it. I mean, usually there are multiple ways to test, but one of them is most easiest, time consuming. While others are just time consuming, like the usual test. All right. Then what is the comparison test? Okay, so let us say we have A series, B series. Okay. Well, actually, it's not. Okay. It's nothing about the series. It's the term. Each term by term, an is smaller than smaller than then what do you have?
And Bn converges.
Okay, so Bn is convergent. Will give us. Okay. So what if? So what about divergent? Right. So if An is term by term smaller or equal to Bn, then the bigger one, if the bigger one is convergent, the smaller one has to be convergent. It's like but it's have that view. If the smaller one is divergent, the bigger one has to be convergent, divergent as well. Okay. So what about the limit comparison test? It's also about two series, right? Okay.
When they both converge, they both diverge.
Okay. So there are both convergent or both divergent. You see it's not. So it has to be greater than for both either convergent or both divergent. And remember, for this limit convergent test, there's no larger one, no smaller one. We just have two. We just have two series, and we divided. A don't have to be always greater.
Okay.
Has to be positive. That's the first step using this test. The term of the series has to be all positive. So now we can move on to next test, which is called alternating series test. Right? Now we have something, the term of the series are alternating positive, negative, and positive. Right? So what about this test? Anybody remember? It's so cool, right? So if you better remember it, so what about it?
And or the function and the n plus 1 over n.
Okay, so
Summation can have n negative 1 to the n and or the yeah.
Negative, positive, negative. But if it's positive, negative, it's the sum of the infinite sum of negative 1 to the test to the limit of the absolute value. We're multiplying negative 1 to the
it's something like this, right? So it's if we started from 1, then the first term is positive. Okay? So it's B1 minus B2 plus B3 minus B4. Okay? So what is the test for when the series is convergent? The limit, which limit? So the last term, right? The B of n has to be have a 0 limit, which is actually the test of divergence, the first thing, right? So this condition is kind of given in case that it has to be convergent, right? So what about the second condition? Well, actually, in the book, this is the second condition. So what is the second condition? Yes, yes. But in order to apply the alternating series test, we have another condition. You mean here? Oh, here we assume that for all the term are greater than 0, that's how we, write alternating, plus minus plus. So this really is the term gets smaller and smaller. The term gets smaller and smaller. The absolute value of the term, of course. I mean, if you're writing like this, you know, all the terms are smaller and smaller, but you see it's if you know, writing like this, you know that B1 is greater than 0, B2 is smaller than 0, so the test should be B2 smaller or equal to B1, okay? And of course, that's not the only, you have to check the n plus 1. Okay. When you apply this, yeah, so this test is really useful. Like, there's gonna be one of the problems that has the argument term. You're gonna use it.
Also, like,
And there's smaller piece. Yeah, this is the one. And finally, we move on to the most important thing, the ratio test.
oh, yes.
So not only the ratio test is very convenient and sufficient, but also for power series, almost all the power series we use ratio test. And somehow we can, use the roots test. Okay, but ratio test is of course the most important. You guys remember the ratio test?
Yes, sweet.
Okay, go ahead.
Ratio test would be the limit as n approaches infinity, which would be the absolute of
Okay.
an plus 1 over a.
Okay. No, I'm not. Okay, then what is it?
Oh,
We check this, right?
oh, yeah.
We check it,
Yeah, R.
right? Yeah, we check this. If it has a limit,
If it's greater than R, then the I go to, or if it's less than R.
hard,
What?
Oh,
1, right? So you do 1. Well, R is the radius of conversion. You're gonna find what R is.
yeah.
You use smaller equal to 1 to figure out what R is. You're gonna see the problem for the problem.
What is going on here?
Yeah, I'm confused too.
I-
What?
Okay, so.
Why is there L?
I was just a sublimit.
Limit is equal to some number, L,
Oh,
we use
it's just
R
some
in
number.
class. And so we're just.
I'm not confused about the
You guys use R in the class?
Well, that's what, well, in our notes, our major head is like R. Well, it doesn't matter. I just want to know what that was.
Okay, so it takes the limit of an plus 1 over an,
Okay.
and R, it equals R, and if R is less than 1, then it converges. Okay, that's what it means.
All right. So what if R greater or equal to 1 or even infinity? Okay. So remember clearly, I mean, these are the things that are like, people start only.
If it's equal to infinity, then we try something else.
Yep.
Okay,
Not-
no?
What?
It's divergent?
If it equals R, it doesn't exist.
Yeah.
Although, there's an argument that it doesn't.
But if it's greater than 1, it's divergent.
Yeah, so infinity is greater than 1.
Oh, yeah. Yeah. Infinity is greater than 1, so it's convergent. Got it.
Okay. So if R is smaller than
No.
1, is convergent.
Yeah.
Right?
Yeah.
Wait, so it means it
So then it diverges.
Greater than 1. If it's 1.
Yeah.
Yeah.
Yeah, if it's
One,
1,
you have to do something
Yeah.
else.
Exactly. Close to 1, then you
Infinity is divergent.
This is divergent.
Yeah.
This is convergent.
Yeah.
Yes,
Yeah.
yeah.
This
We have to do another
You know,
test.
is
Okay.
inconclusive. So when I learned it, I just remember this gave me nothing, right? Nothing, right? All right. Similarly, the root test is really
Such a good movie. It's such a good movie.
Hang on.
I'm sorry, I just love that movie.
okay. So the root test.
Yes.
So what is root test?
Oh, you think the square root is actually
Not the square root,
the
the nth root, right? Okay. Maybe you can do it right, but you just use okay. And now we have if the limit is like equal to L, compare L to 1, and the same conclusion is smaller than 1 is convergent. If it's greater than 1, even infinity is divergent. And we go to this conclusion. Alright? So now, since this is the, you know, the most, since this is the most important thing in this chapter, and maybe the most important thing, I think it's the right time to do some practice. Alright? Okay, so now first a problem. This series convergent or not? If you finish this one, you can start with the second one, which looks horrible. If this here is convergent. Do you have anybody get an answer for the first one? Divergent or convergent? Divergent? Why?
movement as n over n plus 2 approaches infinity. It equals one.
Okay. Alright. So the limit equals to 1, does that, right? So while we don't care if it's 1 or not, it's just not 0, right? So it's divergent. Okay. And what about second one? And now we have a third one. the problem is whether the students are awarded. Okay, anybody can answer for the second one? Is that worded? Why? So first thing is what task we are using. Ratio has heard. Okay, so what is the ratio? Excuse me? But it's product. So let's just say we use the ratio test. What we got?
The quantity of cake plus points.
Alright.
Times E to the cake. Is it native cake plus 1 or native cake minus 1? Yeah, it was, yeah, it wasn't that. Oh, and then, yeah, yeah, I think so.
Right?
Yep.
Okay, then this two, the one we have here. So limit k to infinity k plus 1 squared over k squared, right, times 1 over e. Right?
Oh,
So what's the limit of this part, the first one?
that would be 1.
Right.
So that's,
Exactly. So E is something like 2.7 or something. So 1 over E is smaller than 1, which really means by the ratio test, this series is covered. But remember, this also can use the integral test. But we don't do that. You're gonna use integral by part twice. Actually, I do it. You're gonna integral by part twice. So you're gonna find out the same thing, but we can also use the ratio test. That's why I said you can use the integral test. There are always maybe apply the ratio test. So what about the third one? Anybody have an idea? If you finish this, we can try
What is that on the?
an tutorial. Any idea they're on a tangent then? I guess the first problem is we don't know what task we're using. Yeah, that was a task doesn't work, and we can use the lesion task, right? And what we got? A integral task? No way. Yeah. So maybe and it's not alternating, right? So we left, work on that. Comparison. Right? So what to compare with? Well, it's kind of like we have to make an assumption first. If it's converted, like if converted to assumption, we have to compare with something converted as well. Right? And then, but tangent is we don't know like much about tangents. We got to apply something that we know. Okay.
Yeah, it's not
You
just
were
like
just say divergence, right?
Goson's finished.
So do they both diverge?
Like
Yeah. Let's rewrite it.
oh, yeah, no, it was interesting.
Well, tangent goes to
Tangent's like-
infinity.
Yeah.
So there's no way but so we can make a assumption this is like worded.
Yeah.
So what to compare with? Tangent of things. Then how we but how can we compare this with tangent? Exactly. Okay, so limit converted, what to compare with? Is working. I think this is is there anything familiar with this? Familiar with this? Is there what is the number one example for divergence? Okay. And we have one over there here, right? Maybe the question is why did you try it? Okay. So it's like this, right? Now the sine tangent is sine over cosine, right? So it's sine over n over 1 over n.
The nth root of 2. Okay.
Word is too smart.
And then that's to the, it's equal to the limit of n as n approaches infinity of 2 raised to the 1 over n,
Okay.
which would be,
0. Okay.
yeah, 0.
What it gave you? Give you nothing. Yeah, that happens a lot. Like after all the works, it gives you nothing. Like the ratio test, the root test, or even this test for divergence. So we still don't know if it is divergent or not.
Equals 0? Okay, so if it's equals 0, okay. And then if it's greater than, yeah,
Oh, it's just
not 0, then, okay.
Yeah.
Okay, so equals not 0.
Okay, comparison test. So what to compare with?
seriously, why would you do because we figured out the first one.
Oh, you want to compare with that?
No.
No.
That's one
We need
part
to
that
find
does
something to compare, like 2 to the 1 over n. Something similar to that. We don't really care
Well,
about the negative.
Okay. So here we got this step, right? We don't know what to do. We priority we can. And ratio has of divergence, or even it's not seriously not alternating, or anything. So we're gonna try maybe comparison test, right? So what to compare with? Like I said, what is the number 1 example of divergence? Okay, so in order to make it divergent, what we need isn't that this formula has always to be greater than 1 over n. And so it's term by term bigger than 1 over n. If this divergent, then this divergent. Okay, so remember here we have a 1 over n here, y over here. That's why we compare it to 1 over n. We're gonna check, right? So things like we define another function, right? Fx equals to 2x minus x minus 1. Okay. What are we doing? If we plug in 1 over n, that's the formula right there. Okay. So, and to remember the domain of this function becomes n greater than 0, x greater than 0, small or equal to 1, right? That's the domain, that's the range for 1 over n, right? So, what is the first term? F1 equal to what? What n equals to 1? F1 is 0, right? Okay. So, how we decide if a function is increasing or decreasing? derivative, right? So what's the derivative of x?
Yeah, using here, right? X times 2 x minus 1 minus
No, this,
oh, it would be x.
what's the derivative?
Wait, what formula actually for the yeah, which is 2 to the x minus x times 1. Yeah.
So a to
A of x
right?
I'm just gonna shut up.
Right? That's right.
Yeah. It's a constant, you pull the constant.
But when
But x
does
is
it-
2 to the x, right, is not the same as x to the 2. You're thinking about e, that's where you're getting confused. If it was e to the x, it's its own derivative.
because of L.
okay, no, I was saying is why don't you drag x down?
No, it's not.
No,
Do that for
no,
constant.
yeah.
I mean,
Because x could be 1, or x could be 2, or x could be 3, it's not a constant.
Okay, but still, well,
No.
Just
okay.
the rule, it's just the rule.
I think I can improve it for you, but it's gonna take too long.
No,
Yeah,
no.
just keep going.
I'll just have
We have to
them.
remember
Okay,
that
just remember, alright? Just remember.
Yeah, I mean, I
If
know.
a is a constant, x is a variable, right? Not the other way around. This is a polynomial. This is a log. No, it's convention.
Oh, now I remember.
Here we go.
Okay, there you go.
Now I remember, that's right.
Okay, so now what's the derivative? 2x ln 2, right? 1,
That makes sense.
right? For x between 0 and 1, is greater than 0, right? So this is actually increasing. That's how we get this is always greater than 1 over. So by comparison, that this is yeah, because 1 over n is that way, and something term by term greater than 1 over n is also derivative. I don't know how difficult it has been, but but these are actual examples in the book. I just picked them, like, I want you to experience as many as, ways, right? See, we literally use all the tests, right, for this other problem. So, I hope this will help you. Probably. Right? So now we move on to the third part of this chapter, which is power series. And of course, there are Taylor series and Maclaurin series. Right? So what are the definitions for a power series first? What is it like? It's the summation from 0 to infinity, C of n, which are the coefficients, times x minus a to the n, and a is the center. Right? So, how many scenarios are there for this power series? the convergent or not. Or maybe using the technical term, the radius of convergent. How many scenarios are there?
It can convert it from like all numbers.
Okay.
Negative infinity to infinity.
Okay, so for all x is convergent.
Yeah.
Then the radius will be, okay, the radius is infinity.
Or it can just convert them.
Okay, so only x equals to a, the radius is
A.
here's a, here's x, right? Here is x minus r. Okay. Here's x plus r. This is the interval of convergence. And the r is the radius of convergence. So when rx can only converge at a, the radius is 0. Exactly. X minus a is in the radius of r, which is among the case that we encountered. And we're gonna try to figure out what r is. Right? So that's our problem for power series. And in particular, we have two important series, which are called Taylor series. And the special case for the Taylor series is Maclaurin series, right? So what is the general formula for Taylor systematic?
X times 1 x minus a raised to
Right? Okay, so what is the Maclaurin series?
That's, something equals
A. Yeah, so
something
she
Okay, so when a is 0, it becomes the Maclaurin series.
yeah.
Okay. And the professor also mentioned there's a Taylor inequality that r of x, which is it called recession or the error? This one? Or something like that. It's always smaller than m, which is a bounded number. I mean, for this case, he told me that don't worry about the application while asking physics or something like that. But maybe there's a problem about the approximation of the series, and let you figure out how well this approximation is using Taylor inequality or the task we used before. I believe that's in the task book, right? Okay, so there's gonna be something like this, or not, but you told me to mention, right? Okay, so basically, that's all the things that we need to know, right? We can do some problems about it. derived from scratch. What is the Taylor series for E of x? E to the x. How we do it?
Oh, you take the, don't you put it closer to the person?
Right. Lawrence series.
Okay.
So in order to find out the Maclaurin series, we have to find out the corresponding coefficient, which is the derivatives, right? So this particular problem is really easy because derivatives are all the same. They're all e to the x, right? So all of them equals to 1. So really, the Maclaurin series for e to the x is 1 plus x plus 1 over 2 factorial x squared plus da da da, which is, or maybe one more time, 1 over 3 factorial x cubed, right? So you can generalize by saying something like, okay? That's how we will derive the Maclaurin or even Taylor series for some functions. Okay. If you have time, do the same thing for sine x, cosine x. Well, there's one more thing I need to say about the cosine x. So it's not a problem, it's I want to think. If we have the formula for sine x, can we find out the cosine x without derived from the spread? How? But how? The question is how? When I ask you something like this, the answer should be yes. You know, I mean, how about let's make it a problem? Okay, so we know sine of x is actually n 0. You only keep the odd term. Remember, sine of x is keeping the odd term.
So then you switch it so it being next because of the next sum of negative 1. I was just gonna switch. It.
But that has to do something. How you get it?
Oh,
Is there something I didn't say, like, but covered in the class? How about term by term differentiation, integral, integration? Remember? Okay, so the cosine is really the derivative for sine of x, right? So using this, we have the term by term derivative for sine of x, which is now here's a polynomial. There's no information. Term by term differentiation, so just take the derivative of each term. What is the derivative of x to the 2n plus 1? It's 2n plus 1 times x to the 2n, right? They are just all constant. We can even plug them out, right? So let's give us x to the 2n, 2n, 2n. Okay? Just remember, sine, you keep the odd term, 1 plus 1. And the cosine, you keep the even term, 2n. And sum them up. Well, not just sum them up, you're gonna find, but not just sum them up, alright? You have to remember, like, for e to the I, sorry, I don't know my pen. Do you have any minute? Yes, do you have some problems? Well, it's about determining the radius of convergence. I think that's another important thing for the test. Find the radius of convergence for this series, and also find the interval of convergence. Remember, there are two different things. But how can you find out? Is it what? Okay, ratio test. Okay, so what's the radius of convergence? 1?
No, well, well, if you said the question,
It's not right.
It
it was
is,
one.
That's fine.
it is 1. It is 1. But how we get it? We use the ratio test, right?
Yeah.
And an plus 1 over an absolute value, which is x to the n plus 1, right? 2n plus 1, right? Times 2n over x to the n, right? Oh, sorry, my bad. Okay, so
Oh, okay, I understand. Sorry. Go.
sorry, my bad. So this gives you 2n plus, right? So becomes 12. We don't need the absolute value anymore. It's x times 2n minus 1 over 2n plus 1. This is 1, right? Oh, sorry, we do have to use the absolute value. Sorry, we don't know x yet. So this really is just the actual value of x. But the ratio test has to be smaller than 1. So that's why R is 1, right? So what about the interval of convergence? Right, so from this we get the interval of convergence something like this, but we don't know the behavior for the endpoint yet, right? So we have to check for x equal to minus 1 and x equal to 1, right? Then we plug it in. So for x equal to negative 1 here, if you plug it in, is it convergent? So now the problem becomes if comes close, right? Yeah, it's alternating series. We use alternating series test, right? It's alternating. The last term comes to 0. This is 0, right? And the term is getting smaller and smaller, right? So 1 over 2n minus 1 is smaller than, sorry, is bigger than 1 over 2 times n plus 1 minus 1, right? So that's the two conditions for alternating series test, which is the last term goes to 0, well, not the last term, it's just the limit of the last term goes to 0. And the terms get smaller and smaller. So we know x equals to negative 1 is actually make the series convergent. What about x equals to 1? Okay. Okay. So this is convergent? Yes. You can compare it.
One is greater than 1 over x, 1 over x diagonal. So that's what I want to say, do the comparison test. Yeah, yeah. Right?
No,
Yeah.
because you have to use.
So
Oh,
let
right, because it's decreasing that it's never mind.
No.
well actually this is not greater than 1 over x. Well, n is larger is smaller, right?
Yeah.
Let's just say n equal to 10. This give you 1 over 19. This is 1 over 10. So,
Smaller.
but you can use the limit comparison test. Over 1 over n will give you the limit for 1/2, I believe. Yes. So 1/2 is a number which is not 0. So by limit comparison test, 1 over 2n minus 1 is still that way. So we cannot include x equals to 1, which means the interval of divergence is really something like this. Okay. Okay. I guess we can move on to the final problem, which is not necessarily hard. Oh, there's the 2 problem. Okay. So what about this? What test were you using? Right? Okay. So it becomes the limit n to infinity x n plus 2 1 and 3 times 2n minus 1 times 2n plus 1, right? Times 1 and 3 2n minus 1 over x to the n plus 1, right? So we can simplify it. We get x over 2n plus 1. So, what is the radius of convergence?
But it's probably not here.
Yes,
Zero, that means the rate, the raise will be.
exactly. Because the limit is 0 no matter what. Like, for any x is still 0, right? So, the radius of convergence for x is infinity. Right? It works for all of you can check the Maclaurin series for e to the x, and yeah, e to the x is has the infinite radius of convergence. So now, I really like this problem. So let's make it a last one. Okay. So somehow we know that yeah. Somehow we know that this series converges. Okay. So what can we say about this one and this one? So the assumption is this is convergent. So the question is how, what do we know about those two series? Like, are they convergent or divergent? Or even we don't know.
So we're saying that for these convergence, we're allowed to solve for C of N.
You can't solve this with
No, no, no. C of n is just some parameters for this problem. We just know that for this this set of C of n, this series is convergent. So we are using the same set. We say something about this two series and with the same parameters.
their are they? Again.
It's an alternate series, so at some point it switches off into greater and lesser.
It's getting larger and larger. It's getting larger and larger.
The second one will be convergent as well because it's less than C of 4N.
But
Even if it alternates, it's still less than C of 4N.
That's good. But we have to use some actual proofs.
oh,
Oh, so a logical thing.
Yeah, logic is right.
This is so will a simple comparison test?
Well, I guess.
You simply can't put C of N next to negative 2 and it's less than C of N. I was saying, use comparison test and just write less than.
yeah. Except we can.
Well, I'm glad you brought it up, but the thing is, when we use comparison test, we have to make sure the terms are all positive. Well, that's the common mistake. I'm glad you brought that up.
All right, look at that. Common mistake for the win. So it's an alternating series, so we should use the alternating series.
Yes, but this one we can't because the terms are increasing, not decreasing.
So we can't turn anything using
Then-
that thing is convergent.
Then why don't we use the fact that this series is convergent? All right, we try to do the ratio test. Okay, so limit n to infinity f to value c n plus 1, right? 4 to the n plus 1 over cn for n, which is 4cn plus 1 over cn should be smaller to 0, smaller to 1, right? Well, can we put a equal there? Remember, this is why I like this problem. If it's smaller than 1, it's convergent for sure, right? But if it's smaller equal, but if it equals no, this series is convergent, so this can be 1. So this part smaller equal to 1, which gives us limit n to infinity Cn plus 1 over Cn smaller or equal to 1 over 4. Okay? So we do the same thing, ratio test for the second. Yeah, limit n to infinity Cn plus 1 times negative 2 to n plus 1 over Cn times negative 2 to the n. Give us limit Cn plus 1 over Cn times 2, right? And we know this part is smaller or equal to 1 over 4 by that. Okay? So this is really smaller or equal to 1 over 2, which means it's still converted. And that's why I say logically it's right, because it is in between. Yeah. All right? So now, so what about the alternate series for the original one? The ratio test becomes Cn plus 1 times negative 4 n plus 1 over Cn times negative 4 n absolute value, which becomes n plus 1 for Cn plus 1 over Cn, right? Is still smaller or equal to 1 over 4 times 4 equals to 1. But remember, this is another case. When this limit goes to 1, it's still inconclusive. So it really means it can be divergent in this case. So this series, we cannot say anything about it. It can be divergent or convergent. Right? It's the equal part that makes it a little bit complicated. Okay, I think that'll be all. I hope what I did help you guys in the exam.
Thank you.
Well, you guys sign a manual on it? I don't know if it's required, but